Okay, great. Can you hear me okay?
Yeah.
All right. Thank you so much for inviting me. It's a great pleasure to be here in this audience and to talk about these issues that have been embedded in the Twitter sphere and publicly for a little while now. I'm going to try in my talk to tell you why everything that Conrad said is wrong. And my goal is to speak quickly enough that Mike won't have time to tell you why everything that I said is wrong, maybe just some subset of the things that I say are wrong. All right, so I would be happy to take questions during my talk if you have questions. If it gets, is that okay?
Sure.
I mean, if it gets off the rails, I'll try to focus back because I do have roughly 40 minutes of material here. But if I say something that's unclear or you want to ask a clarifying question, please feel free to step in. All right, so you know, I had to prepare this talk without knowing fully what Conrad would say, so there will be a little bit of overlap. Let's just set the stage. Of course, we're talking about this random dots decision-making task where there are, you know, there's a fixation period, some targets appear, motion epoch is defined where there are moving dots randomly in one direction or the other. Conrad showed you the demo. And then the animal reports its decision about which direction those dots are moving by making an eye movement to one target or the other. If the animal thinks the dots are moving right, he moves his eyes to the right. If he thinks the dots are moving left, he moves his eyes to the left. And there are a couple different versions of this task. One where the animal is allowed to report its decision as soon as he makes it, and another that's called the reaction time version, and there's another version called the fixed duration version where the animal has to wait for a go cue. All right, so everything I talk about data during this motion presentation period, before the animal initiated its eye movement, all right? And the question we're going to focus on today is, what are the latent dynamics of spike trains in LIP during this sensory evidence accumulation period, all right? And so before I go too far, one distinction I want to make very clear, if you take one point away from my talk at all, that I think will do the most to sort of debunk Conrad's talk, it would be this question of what do we mean by latent dynamics? So this is going to come down to a fundamental disagreement about how we're doing model comparison here that I think is important. So let's tackle this as sort of a side issue before we move on to the exact model that we're going to look at here. Families of models that we'll talk about here. So what do we mean when we say latent dynamics? That's a sort of jargony term that people throw around, and I often have the sense that people don't actually know what that means. It feels fun to say, but you know, what does it mean to say latent dynamics? I think one way to think about it is to contrast it with a direct sensory encoding model where we explicitly regress the spiking activity against some sensory stimulus variable. So you can think of that as a model that's defined in the following way. We have a mapping straight from S to the neural responses. And so a classic example of that is like an LN cascade model or an LNP model, where we say explicitly the probability of a spike in some time being given the stimulus is just a linear function of the stimulus. This is K dotted with S, passed through some nonlinearity. All right? This is a model that's very easy to fit to data. This is one of the things that makes it so popular to work with, and it's very tractable. It doesn't take any advanced methods to fit such models. By contrast, when we say a latent variable model, what we have in mind is that there's some intervening stage, X, that mediates the influence of the stimulus on the response. All right, so here I've drawn this X as a scalar quantity that's drawn from some distribution. And what we imagine is that even for the same fixed stimulus, from trial to trial, that latent variable is different on different trials. And latent here means that it's unobserved. So this is stochasticity inside, hidden from us, the modeler. All right, so this is X is something we don't get access to. All we see are S and R, but we're invoking the existence of a stochastic quantity that on each trial comes from some distribution, and that the true generative process of the data is that X, the response depends on the stimulus via this random variable. All right, and so the advantage of such models are that they provide an extremely powerful framework for building models of neural data. And in fact, the classes of models that we're really arguing about today both come from this family of there being some hidden quantity that we want to reason about, but we don't have access to it directly. All we see are spikes, and we'd like to reason about the underlying steps or ramps that may have given rise to those spikes. And so the challenge is, so it's a rich modeling language, latent variable models, but the challenge is that when we want to fit these models to data, of course, all we can fit is the probability of the responses given the stimulus. But computing this quantity is no longer an easy thing to do. Unlike the LNP model, this now requires computing an integral over the latent variable. Oops, sorry. All right, so the model is formulated in terms of these two pieces: the probability of the latent variable given the stimulus, that's P of X given S, and then the probability of the responses are conditioned on X, the latent variable. And sort of to ask how likely a particular spike response is given a stimulus, we have to integrate this over all possible settings of that latent variable that it could have taken under this distribution. All right? Things are actually worse than that in this case here, which is that we don't have a single scalar latent variable on each trial unless you're Conrad, and we'll come to that in a little bit. If we're interested in this drift diffusion model, then we're actually interested in latent dynamics, where there's some changing quantity. There's a latent variable at time t-1 that influences the latent variable at the next time bit. So imagine, and I should say, the temporal dependencies in the spike train here, under this kind of model, are entirely mediated by the temporal dependencies between the latent variable. All right? So this is a latent variable that evolves through time with some dynamics that describe how I get from the latent variable at one time bit to the latent variable at the next time bit. And as a result, the model has this more complicated form here. We have a model of those dynamics, how x of t depends on x at the previous time bit and the stimulus. And then that dynamics model just describes sort of this upper part of the diagram. And then we have an observations model that describes how we get these spikes given the latent variable at each moment in time. And now this involves a high-dimensional integral over the value of the latent variable at each moment in time. Barry, do you have a question?
I'm just wondering why both you and Conrad are not mentioning that the stimulus also has temporal dynamics.
We're ignoring that because, yeah, you're right. So the stimulus itself also, if we thought about modeling the time-varying dot motion on the screen,
You know what it was.
we don't actually because Alex didn't save the dots. So we have the average strength of the dot stimulus. I don't know if Mike has those. I don't think those were online with the data set that we downloaded. But you're absolutely right. We could model we could model this with a regression model where the kicks in this latent variable could be explicitly depending on the motion energy computation on the dots at any moment in time. So we have a more recent version of the stimulus where the motion comes in little pulses, discrete pulses, and it's easier to do those kind of regression analyses. But you're absolutely right. This is, and I should say, we wouldn't have to have, yeah, there are a variety of ways we could set up this model differently, and in fact, of course, the changing temporal evidence through time is something else might want to model. In our case, S is actually just the average motion strength at each moment in time. And we're going to treat the fluctuations through time as latent variables that we don't have access to, which in fact we don't. Great question. Okay, so the 500, so we're talking about these, so this is the family of models we're interested in discussing. Latent variable models, and I hope it's now clear how those differ from sort of explicit regression models where we assume everything is observed and we're just mapping the stimuli onto the spike responses. So the 500-pound gorilla in this room is the drift diffusion model that Conrad very nicely derived for you. And the idea is that the latent dynamics are described by a Gaussian random walk. We have some average, but this is also known as the drift diffusion model with bound. It's also known as the accumulation-to-bound model. Sometimes there's a variant called the race model. And the basic idea is that this latent variable follows a Gaussian random walk with some mean drift, where that mean drift reflects the accumulation of sensory evidence, average accumulation of sensory evidence over time. And the trial-to-trial fluctuations in the path of that latent variable. So this is the distribution of the jumps at each moment in time come from some Gaussian with its mean shifted away from zero, reflect either some combination of this noise in the stimulus, the motion energy that varies from moment to moment, or possibly internal sources of noise that are added to that. Okay. All right, and so as Conrad mentioned, Mike's lab and a variety of others have done some beautiful work relating this drift diffusion model to the activity of single neurons in the area LIP. In particular, you see the striking finding that the slope of the firing rate is steeper the stronger the motion evidence. So when we have strong rightward motion evidence, the average firing rate ramps up steeply, whereas it ramps up gradually when we reduce that, just as we would expect from this classic drift diffusion model. And I want to make one more distinction between sort of the kinds of approaches we're going to think about here. I would say one of the beautiful things about this entire line of work from Mike and Bill Newsom and Josh Gold and many others is that it relates a descriptive model of the data to a normative account of what these neurons ought to do. So there's some optimal theory of decision making that this is really the right quantity to compute, the accumulated evidence for left or rightward decision, and then they're mapping that ideal model, and I should say that's also a model that's been shown to give a very good description of the behavioral data. They're mapping that model onto the observed neural data. All right, and there's a variety of examples of these kinds of normative models where instead of the log probability of one choice versus the other, we might imagine it's the expected utility, posterior probability, changes in the reinforcement learning value function. There's a variety of other normative approaches to asking what would I expect LIP to do under some model of optimal decision making. And our approach differs in that we're ignoring this functional question, where we want to be completely agnostic about what it is, what computation LIP is doing. We want to simply ask, what is the most accurate statistical model of the spike train that we observe from trial to trial? And of course, there's been some work in that area, though I would argue less so. One prominent example, this also comes from Mike's lab. This is Anne Churchland's paper on the variance of the conditional expectation, trying to use the variance of the spike count through time to ask as a signature, a statistical signature for diagnosing which kind of model could have generated the data. Okay, so let me leap into our, so the main motivating point for our work was this observation that the classical analysis of LIP response, the one that I just showed you, was plotting the average firing rate of an LIP neuron as a function of time since the motion came on, and showing that that average firing rate ramps. And so this is a different data set from Shadlin and Newton in 2001, and this is what you can see is a raster of spike trains. Each one is an individual trial. The dots are the times of spikes of a single neuron, and we've aligned that raster of spikes to the time at which the motion came on. And in the individual raster, this agrees with what Conrad said. We can see that there's a lot of sort of stochasticity. But if we average these time-varying spike times, we get a PSTH, an average firing rate that ramps up through time when the motion is into the preferred response field. And when it's out motion, we see something that looks either flat or with a slight downward slope. All right. And so I think one interesting thing to think about, of course, is the fact that this picture from the PSTH is not enough for us to make definitive conclusions about which model generated the data. So if I wanted to know what happens on a single trial, so this single trial spike train, this averaging process to compute the PSTH obscures the single trial dynamics that might have given rise to this spike train. In particular, we can imagine two different kind of latent processes. This should be review for those of you who paid attention to this literature. The noisy ramping model or drift diffusion model is one in which we postulate a time-varying Gaussian random walk that I just described to you, which has an average upward drift. But another way to get an average that looks like a ramp would be with a discrete stepping process where in each trial I have a step from one lower firing rate to a higher firing rate. If those steps happen with different times on different trials, then the average of these steps could also look like a ramp. And so our goal is to design some powerful statistical machinery for testing these two different models of the data. All right? That's the setup. Let me now review I'll try to briefly review our first paper, our first entry in this literature. Any questions so far? Great. Okay, so in this paper that we wrote with Alice Hoff and Kenneth Latimer, who was my PhD student who led all the work, very, very gifted student. He's now a postdoc at the University of Chicago with David Friedman. We wanted to build we wanted to do explicit model comparison between these two classes of models. So the first thing to do is to try to make our best attempt to specify exactly what we mean by the drift diffusion model. So here's how we chose to parameterize that model, and you could criticize the way we chose to do so, and in fact, Mike has, and I'll talk about some of those criticisms a bit later in the talk if I have time. This was our best effort to take what was described in the literature as the drift diffusion model and map it into something that we could explicitly fit to data. So the model is defined, this is the sort of picture of what the model would look like. It's defined by an initial spike rate. There's a bound height spike rate, which is the absorbing boundary for spike rates. And this beta sub c is a slope of that increase in firing rate. And it depends on the coherence. So sub c indicates that for some coherences, this could be a steeper slope than on other trials. And what do we say is that on every trial, we're going to get the latent state evolves according to a Gaussian random walk. So we have x of t is equal to x of t minus 1 plus beta. So that's the slope per unit time plus some noise. So the other parameter is the sigma squared here, which determines the variance of that noise. All right, so this is a model of the latent process, and then the second part is the mapping from the latent process to the spikes. And we're just going to assume that that's a Poisson process. All right, so here's a single sample of the latent. Here's a simulated sample of a Poisson process with this time-varying rate. Here's another trial now. We'll get a different latent trajectory. We'll get a different spike train. And we can do that over and over again to build up a data set simulated from our model. I'm just showing you simulations from the model to give you some intuition for how this model behaves. All right, so that's all at one coherence level. If we then have a different coherence, so beta 2 could be a shallower slope, let's say when the emotion evidence is less strong. And we will now have trajectories that on average take longer to hit this bound or maybe never hit the bound by the end of the trial. And these are the Poisson spikes simulated from those trajectories. And this is consistent with what Conrad said. Looking at these spike trains here, it's very hard to see on any single trial what latent process generated them. We only have access to that because these are simulated data. In real data, of course, we're trying to reverse this model and take the observed spike trains and do inference over these latent trajectories. Okay, so that's the drift diffusion model, which I'm casually referring to as the ramping model. It has 8 parameters. There's an initial firing rate and a bound height. There are 5 different slopes, one for each of 5 coarse coherence levels, from strong rightward to strong leftward, and then there's a variance of that Gaussian noise. That's model 1. The stepping model, on the other hand, we parameterized a bit differently. In this model, there are only 3 spike rates that are ever observed. There's an initial firing rate, an upper firing rate, and a lower firing rate. And then we have a distribution which is called a negative binomial. This is the discrete alternative to a gamma distribution, which has 2 parameters which would describe the times at which steps might occur. All right, so we sample a step time from that distribution on any trial. That has 2 parameters. R is the shape parameter. P of C is a parameter that will determine where the mean is, which depends on coherence. And then the probability of an in-step is another parameter, pi sub C. So on some coherences, we're drawing a time from this distribution, then we're flipping a coin with probability pi sub C, and if that comes up heads, we have an up step. If it comes up tails, we have a down step. And we then have the same model spiking as Poisson given this latent rate. So there's a single sample of the latent, here's a spike train sample with that Poisson rate, here's another trial, right? So here's 4 simulated trials from the stepping model, and these are the spike trains. The result, we can imagine that for some different coherence, we have a different distribution over the times of these steps, and we can simulate the spike. Here we actually had pi sub C for that coherence, all resulted for all 4 of these trajectories in a downward step. And again, by eye, it would be hard to, you can probably tell that the blue spike rate is a bit slower through time, but it would be hard to identify from a single spike train when exactly the step occurred in that neuron. Okay, this model has 14 parameters now. It has an initial firing rate, an upper firing rate, a lower firing rate, and then these pi's. For each coherence level, we need to know the probability of the coin coming up heads. That's the probability of an up step versus a down step. This parameter which determines the mean of that step time, and R is the shape parameter that's global across parameters. So 5 parameters and 5 parameters, that's 10, and then 4 more of these other parameters. Okay, so those are the 2 models that we wanted to work with in our initial paper, this 2015 paper. And of course, fitting these models to data is difficult. As I said, it involves, actually, all we observe are the spike trains on a single trial. We want to compute the probability of this spike train given the coherence, that's the stimulus on that trial, and the model parameters. This is either the 8 parameters from the DDM or the 14 parameters from the stepping model. And computing that probability requires integrating over all possible latent paths consistent with those spike trains. All right? So this is a high-dimensional integral, as I mentioned in my early slides. And so it requires some complex machinery. So this is the integral we're doing. The model specifies the spike probability distribution over the latent variable and the spikes. And we have to integrate that over the latent variable, which we haven't observed, in order to ask how much probability does this model assign to the data. All right, and so Kenneth did a very nice job building some computational tools with Markov chain Monte Carlo to compute this integral in order to sample the parameters of this model. Okay, all right, so any questions so far about the models? That's the sort of description. Okay. Those are the 2 models that we'll start with. Let's now think about, let's take a break and ask about how are we going to perform model comparisons. So this is a bit of a review with Conrad's talk, but hopefully I'll cover things in a little bit different order than he did. So we want to now ask which model is better, right? We have this 8-parameter model and a 14-parameter model. Which model should I prefer? Which model should I say for each cell is a better model of what that cell spike trains were? All right, so naively, of course, more parameters is better, right? If I just gave you this sort of cloud of blue points and asked you to fit a model to it, a constant would give you 1 fit. If I give you 3 parameters, you can fit a quadratic. If I give you even more parameters, you can fit the curve through every point on this, every one of the blue points. So naively, if you add parameters, of course, your ability to describe variability in the data grows. But obviously, if you use too many parameters, you will overfit the data. So in this case, our curve goes through every single data point, and that's probably reflecting noise in these particular samples. In this case, it might be that the optimal model in terms of predictive performance is one which doesn't perfectly fit the data, but treats these discrepancies between the blue points and the black as noise. So we'd like to solve this problem. Where along this model continuum, from simple to very complex, should we land? All right. So there are 2 popular techniques for model comparison, and Conrad focused on this first one, which I'm going to delve into a little bit because I think there are a couple different ways to do cross-validation, and this is important to considering what kind of answers you're going to get. So one popular approach, and this is partly popular in the machine learning literature because it doesn't require, it seems it's sort of doesn't require distributional assumptions, or it seems more free from distributional assumptions than the other kinds of tools that people tend to use. The simple idea is you're going to fit your model on some training data, and then you're going to have some held-out test data that you've never looked at, and you're just going to ask, how well does my fitted model predict the held-out data, right? So this is what, we're going to divide the data into a training set, X-train, and a test set. Let's say we're just comparing these two models. We're going to fit model 1 by maximizing likelihood, fit model 2 by maximizing likelihood, and then we will evaluate how probable was the test data given the fitted parameters from model 1 or the fitted parameters from model 2. All right, that's the simple idea there. An alternative, of course, are these sort of methods that are often known as information criteria. They really come down to penalized log likelihood. So instead of dividing the data into a training and test set, you effectively compute the log likelihood of the data under each model, and then you penalize the model based on how many free parameters it has. So this is the AIC, which is maybe the most popular of these. This is -2 times the log likelihood of the data given the fitted parameters. This is now fitted to all of the data. Plus a penalty which depends on the number of parameters. So more dimensions, more parameters would increase this penalty. And so the AIC method works by computing the AIC for each model and then selecting the model which has the lowest AIC value. All right. And I should say there's some theoretical justification for these. AIC tries to estimate the information lost when one model is used to represent the process that generated the data. An alternative is the BIC, which has a little bit of a different form. There we had 2 times the number of parameters was our penalty. In the BIC, this is related to the number of samples as well. So more data means you're going to pay a higher cost for using more parameters. And this is an attempt to approximate the marginal likelihood of the data. All right, so these are 2 sort of well-known model comparison metrics. In our paper, one problem with using the AIC and the BIC is that they require having a maximum likelihood estimate of the parameters. So you're assuming you took the data and you found the single setting of your parameters, which was the best fit to all the data. And we didn't have that in our case. We used Markov chain Monte Carlo, which provided us with samples from the posterior over the parameters. So it reflects the fact that our best guess of the parameters might be in one location, but we still have some spread in our uncertainty about the actual value of the parameters. And so deviance information criteria, this was introduced in 2002, it's a paper with over 9,000 citations, is an analogous to the AIC and BIC, but it's designed to be used with MCMC, where we have samples from the posterior instead of a single maximum likelihood estimate. And it has a similar form. It's got one term, which is the log likelihood of the data, plus another term, which is the penalty based on the effective number of parameters. And the thing is about this approach is that we can evaluate it using samples from the posterior over the parameters given the model. Okay. And as Conrad mentioned, that's what we used in our paper. We used the DIC, and we found this result that more of the cells were better explained by the stepping model than by the ramping model. We got a similar result when we applied this to data from Rutgers and Shadlin in 2002, which was a reaction time version of the data set. In this case, we selected 13 cells that had the highest choice selectivity, and we found that of those cells, 10 out of 13 were better explained by the stepping model. Now, one thing you might wonder is, of course, does this procedure even work? We can check consistency of the method by simulating data from the fitted models, and then asking whether when we apply this DIC method to the simulated data, does it get the answer right? And largely the answer is yes. So here's simulations of a ramping model, and we compute DIC. All of these values are negative except for a few mistakes right here in this first. There are a couple cells that came up slightly on the step side. On the step, when we simulated data from the stepping model, we found that all of the cells were correctly selected as stepping. All right. So you might worry that there's a slight bias towards stepping, and in fact, that is what we find in later analyses that I'll tell you about in a little bit. David Zoltowski, who's a student in my lab right now, has followed up with a more recent model comparison information criterion called the Watanabe Keiki information, or WAIC. And this is a little bit more conservative. It finds that 26 out of 40 are better fit by the stepping model. There's still a majority, but a few have moved over onto the ramping side. So this is a newer method which tries to correct some of the overfitting that happens in the case of the DIC. Okay, so that's my summary of chapter 1, where we were with this after Kenneth's papers. We've used this DIC approach. We're now working on the WAIC as a way of comparing these two classes of models, but a lot of interesting results, other developments have happened since. Okay, so next, I'd like to talk about the content of Conrad's paper, which was just released on the archive earlier this month. In fact, I don't think I knew he was joining this debate until about 3 days ago, so it's great to have an opportunity to talk about it here in a public forum. I think one of the motivations for Conrad's paper was to say, well, this DIC that you mentioned, it requires sampling from the posterior, it's computationally intensive, it would be hard to code that up from scratch myself, and so why don't we, is it possible to take a simpler approach? I'm going to tell you the answer is no, but bear with me and let's see. All right, or I should say, it is possible to take a simpler approach, but not the one that they took. Okay, so let's talk about cross-validation. So I agree, actually, that cross-validation is actually a far more intuitive measure of performance, right? There's something more satisfying about thinking I fit these two models with some data, and I didn't even look at the held-out data, and I just asked which model can generalize better. All right, so the way that I would argue that one should do cross-validation for these kinds of data is to divide your data into a set of trials that you would use for fitting your model, and then hold out some of the some additional trials and use those for test. Okay? So this is what I'm going to call a cross-trial cross-validation. So we're going to fit some parameters to the training set. This is simulated data from a step model, just to show you what it would look like. So imagine in the training set, the data really came from a step model where the step was a random variable it was a latent variable on each trial. In this case, we want to fit the parameters. Those parameters are just the lower and upper spike train. X, however, the time of the step is a latent variable. So computing the probability of the spike trains given theta involves integrating out the step time. Okay, so we're fitting two parameters from our training data, and then we're going to use that to evaluate the test likelihood. How likely are these spike trains, the probability of these spikes, given my estimated parameters, the lower and upper spike trains? Again, this involves an integral over that latent variable. We don't fit the time of the step on each trial, we marginalize it out. And we would then, of course, compare this to the probability of those test data given some theta 2 for a different model. Say the ramp model, we would do a similar kind of thing. We would fit the ramp model to the training data and evaluate its test performance right there. Okay? This is not what they did in Conrad's paper. And, instead, what they did something which we will refer to as within trial cross-validation. So they took each trial and they grabbed 10% of the time bins from that trial and they held those out as test data. All right? So all of the red here would indicate the training data that was used, and what was held out were these single time bins, so 10% of the time bins from each neuron's each neuron. And so far, this seems fine. The problem comes into how they fit their data. So instead of fitting the parameters of the model, they also fit the latent variables. All right? So in fact, what they did is they fit for every trial. They fit not only these global parameters, the minimum and maximum spike rate, they also fit the step time. So they maximize the probability of the spike train data given the step time and theta. So if you have 100 trials, this is a model with 102 parameters. So we've jumped from a 2-parameter model to a 102-parameter model, and I should say I think the mean number of trials in this data set was 106. So we're talking about, the argument was that this is a simpler approach. I would argue we've gone to a much more complicated approach, given that we're radically increasing the number of parameters that we're fitting to data. And then they evaluate the test likelihood for these held out bins, the probability of the spike counts of these bins, given the fitted step time for that trial and the estimate of the model parameters. And you can substitute in the fitted step time for the fitted slope or the fitted baseline firing rate for that trial. Okay, so the problem, of course, is that this within trial method won't actually work for simulated data. So here's the simulation that Conrad already showed you. I think one thing he didn't show you is what the true simulation came from. It wasn't the low SNR regime. It was the regime where the step model had an initial spike rate of 40 hertz and it jumped to 80 hertz. So the spike rate doubled. These were high spike rates. I would argue that this is not the low SNR regime. Conrad said if he increased the spike rate an additional 50%, then he would get the right answer. But I would argue that you should already be able to get the answer if you're stepping from 40 hertz to 80 hertz. And of course, this is the result that they got, that Kenneth got in his simulation. The ramp was better for 84% of the neurons that were simulated from this stepping model. So it's got an 84% error rate. If instead we used a cross-trial cross-validation, so we held out some trials and we marginalized over the latent, it has a 0% error rate. So the same exact idea of using cross-validation, it's great, but we should integrate out the latent variables instead of fitting them. Doing so allows us to fit a model with only 2 parameters instead of fitting a model with 100 parameters. And it's that overfitting that's basically, I should say, cross-validation is great, but it still has biases, especially in the case of overfitting. The guarantees about cross-validation working are all in the limit of large amounts of data relative to the number of trials, number of parameters that we have. So I would argue that when we want to focus on cross-validation, we should move to a cross-trial cross-validation. So let me just summarize my take on their paper. So they did within trial cross-validation. They fit models with more than 100 parameters for many neurons. There's a ramp or a step for each neuron on each trial. The advantage of this approach is that it's simple. The disadvantage is that it's wrong. It can't identify the true model in a lineup. So we're not talking about examples of model mismatch, which of course we worry about. I would say that one of the desired features of any model selection metric is that if the true models are present, if the data actually came from one of the true models, it should select that model. And so across-trial cross-validation can do that. Within trial cross-validation can't do that. And the reason, of course, is that it's overfitting to the data. Sorry. The other perplexing result, of course, is that, as Conrad mentioned, this I would say, ill-advised procedure selects the constant firing rate as the best model of these data. That should also give us pause. That can't account for the PSTH. This is the average PSTH from this data set. These are not neurons with no SNR. This is the average firing rate started around 35 and rose to around 60 hertz. And yet, you're saying that the best description of this data, according to Conrad's model selection procedure, was a model that said, on every trial I have a different constant firing rate. Okay, so the take home for me is that it is hard to get anything useful out of models that are badly overfit. So you should think carefully about how many parameters you're fitting to your data. In this case, we're comparing two models with hundreds of parameters, and I think we're down in a regime where it's hard to get useful. Basically, as Conrad said, the constant model is simpler, and so it's overfitting less than the model with steps or ramps. All right? So cross-validation is great, and I'm excited about this idea that there could be constant variability in firing rates across trials. That's something we haven't yet incorporated into our models. But we should do that using a cross-trial validation. So fortunately, a cross-trial cross-validation, which involves integrating over the latents, can overcome these problems. It is computationally more intensive, but it was actually a very simple 1D integral for this case. So nothing fancy was done in that example that I just showed you. You can fit only 10 parameters to the entire data set if you have this drift diffusion model or our stepping model. And you can identify the true model in a lineup, as I showed you. Here's some recent results from David Zoltowski showing that if we use cross-validation on, this is the Meister data set. We compare a constant per trial to a model with a step. We get every one of these cells except 3 is better explained by a stepping model, and the step is better than the ramping model by 22 out of 40 are better explained by the stepping model. And I should say this also, and I agree completely with Conrad and Weiji's statement that we should use multiple models and comparison metrics. Here's a comparison of WAIC, this new information criterion, and cross-validation. This cell is each point here is a single cell in the data set. In this quadrant, we have cells that both procedures identified as coming from the DDM. This corner is all cells that both procedures identified as coming from as better explained by the stepping model. And these points that are in these other quadrants are cases where the two procedures disagree. So they largely agree, and the cases where they disagree, they're fairly close to the boundary. So I think this gives us confidence that cross-validation, at least performed this way, using held-out trials, is consistent. I should say, these are still very different procedures. Cross-validation here involved finding a maximum likelihood fit to the parameter, a single point estimate of the parameters, whereas WAIC was using the entire posterior distribution. So I still think you might trust this more. We could have done Bayesian cross-validation instead of maximum likelihood cross-validation. That might have brought moved these points that are off the edges into the right regime. Okay, so where am I on time? I have 3 more minutes. Is that?
Yeah.
Or am I out already?
You're nearly out, but
okay.
A few minutes.
Let me finish. I only have about 3 more slides. Let's now go back to the issue of the ramping model and its discontent. So Mike Shadlin and some of his collaborators have published a few critiques of our formulation of the drift diffusion model, and I'll talk about just one of those in the last few minutes that I have. So one of the complaints that they made is that our model did not have a lower bound on the firing rate. So in fact, what they said, this is a very nice simulation. If you simulated a process in which the firing rate ramped up to an upper bound or it ramped down to a lower bound, so if the true data came from this model, and you tried to fit it with our ramping model would effectively try to fit this shallow slope because it doesn't know anything about this hard lower bound on the model. And so they said one reason we might have gotten the results that we did is that this process, which is actually a diffusion model, is better explained by this step model because the step model has less error than this approximation with a ramp model with no lower bound. And so they did an analysis where they went into the real data, stochastically removed some spikes to try to adjust the spike weights down to 0. And the take home was that then they found that this data set with 16 cells, which formerly was 13 to 3, is now roughly half and half. Half of the cells now become better explained by step, the other half are better explained by ramp. And so in our lab, we've been working, we thought that was a great idea, and so we've incorporated the baseline. We've extended the original ramping model in several ways. One, we've added a nonlinearity between the diffusion process itself. You could have a saturating or an accelerating nonlinearity between the DDM itself and the firing rate of the neuron. We add a non-zero baseline, and we add GLM spike history. Conrad mentioned they've also done that in their paper. And the take-home is that we get results that are largely consistent. So here's the ramp model with spike history and baseline. This is the y-axis here, is the difference in the WAIC for each of the cells in our population. 14 were significantly better, explained by the stepping model, versus 10 by this ramping model. The ramp model with the square root nonlinearity was slightly better, and we get to roughly half and half. Okay, so this is a rare point of agreement between Mike's group and my group. I'd like to argue, although he may tell you otherwise in a second, that we see whether you use WAIC or you use their simulation procedure, we seem to agree that roughly half the cells are better fit by both of these two alternative versions of the model. So I'll skip this last point. I will say, both of these models are still too impoverished to account for the real structure in the data. So if we look at the real PSTHs, they have more kinks, they have more idiosyncrasies than we get out of either of these two models. They're still relatively impoverished models relative to the kinds of rich structure that we find in neural data. So I think the future direction will be to move towards even richer models. So you might think of one alternative to this, the drift diffusion as I described it, would be a race model where there are two latent variables, one which accumulates evidence for one target, another which accumulates evidence for the other target, and the process stops whenever either one hits its bound. Right, so that would be a richer latent variable model. Or there's a suggestion that maybe discrete states, multiple discrete states, could be better description of these data. And I think when we move to those kinds of data, we want to start looking at multi-cell recording, because obviously across the whole population we'll have much more statistical power for making inferences about what the underlying process was on a single trial. All right, so here's my summary. WIC is better than the DIC. Cross-validation is also great, but please be sure to integrate the latents, don't fit them. I like Zhao and Cording's suggestion to add a variable baseline. This is something that Goris and Neuroscience have also argued exists in a lot of early visual processing. So on each trial, you can have a stochastic baseline that gets added to everything I've shown here. We haven't done that yet, but I think it's a worthwhile thing to try. And then we also looked at a new ramp model with lower bound, in which about half the neurons were better fit by each model. And overall, I think the Bayesian approach, although it is complex and requires some effort to get things to work right, I think it's the right approach for formulating these models and comparing them on rich data sets. All right, so I just want to thank all the work that I described here was performed by David Zoltowski, who's a student in my lab, and Kenneth Latimer, who was my former PhD student now at the University of Chicago, and in collaboration with Alex Huck and Jacob Yates and Miriam Meister. Thanks very much.
Well, now we have questions, and I see.
Great question. So, based on your two-parameter model, essentially you're saying that the best predictor of the trial by trial is the average of the previous trial, correct? That you're essentially saying, I take 10 of 10 trials, I find out the average, and the other two trials are these should be really similar to the average. Is that correct?
So you're talking about the cross-validation procedure?
Yeah.
So no, what it's doing is it's going to fit the parameters. So I should say, in our case, we assumed that we knew the range of, for the step model, we just said we know that the step can be anywhere between the first time in and the last time in, with uniform probability. In those simulations, that's the way we performed it. The only parameters to fit were the initial spike rate and the higher spike rate. Using those two parameters, we now ask, what is the probability of the held-out data that over every possible step time, so uniformly averaging the probability from a first time in, second time in, third time in, over all possible times that the step could have occurred, how well would we explain those data with a process that initially had one firing rate, which we had estimated from the training data, and then stepped to a higher firing rate at the end of the trial, that we also estimated that higher firing rate from the data. We're going to compare that probability, averaged over all possible times that the step could have occurred, with the probability assigned to the same data with a model where there's a possibly different slopes, and we're going to average the probability over a steep slope, shallower slope, over some discrete range of slopes that we selected a priori. So yeah, it's not that we're fitting the PSTH from the training data and using that PSTH to evaluate the held-out data. We're fitting parameters and then we're integrating out the latent variables. So either averaging over the unknown time, step time, or the unknown slope, or the unknown constant baseline.
No, I understand it. But what I'm saying is that There's nothing specific about any identical trial, right? Like I'm assuming what Conrad is doing, taking into the fact that if you happen to be in a higher firing rate state, there is a higher chance that you get this or not get this. But yours said you wouldn't really matter if you're in a higher state or lower state, and you don't know what the stimulus was. You just know the coherence of the stimulus. So there is no information in individual trials in that case.
There's no information in individual trials there's a small amount of information in individual trials. I think there's not enough to fit the step time from a single trial and consider that a parameter of your model. They also tried a model that has constant baseline and steps, right? And those were worse. A model that incorporated more structure was even worse because you're fitting more parameters.
So let me just start what I want to say with one question. If someone's not a Bayesian, can they be right?
I'm sure they can, yeah.
Okay, so
this is a frequentist analysis, right? Where we simulate data. This is not a Bayesian analysis.
Yeah, okay.
We know that a true model exists.
So let me kind of clarify how I view what Jonathan just told us. So as a Bayesian, if we have a model that has a parameter, we should not fit the parameter. We should integrate over all values that the parameter could have proportional to how probable it is there. And at some level, that is a fundamentalist but perfectly tenable view. Now, the disagreement that we at some level have is, should we be fitting parameters for individual values, or should we basically fit every possible value and integrate over it? Which is at some level a detail of the analysis, but it's right, it matters because we're in that low domain, in the low data domain. The problem is by that integration, we are effectively doing a similar thing to fitting the parameter. We just basically fit all of them and like average across them. Now, if we don't believe the models ultimately, we run into the same kinds of problems. And at some level, that Bayesian fundamentalism argument that you make, it's wrong because it's not Bayesian. You can apply that to like any parameter that ever exists. So the argument that at some level, we are over-specified by having little information in lots of trials, that is certainly an argument. But like, it's not specific to this case. It's a fundamental Bayesian versus not Bayesian argument.
I disagree with that. So nothing I did in the cross-validation was Bayesian. So I think you're not acknowledging the difference between latent variables. Hold on. Latent variables and parameters, right? So I did maximum likelihood fit to the parameters. I didn't integrate over the parameters. The latent variables are not
just code.
Latent variables are not parameters, all right? This is the take-home point that I want to make. You don't have enough data to fit every single latent variable from the data, but we can integrate that out. That's a maximum likelihood approach. That's a frequentist. A frequentist would do this as well. So I think if you won't acknowledge that we can have a distinction between parameters that we fit and unknown, in the Goris model, they also integrate over the unknown. They don't fit the modulator for every single trial. They fit the model by integrating that out, right? So this is a fundamental distinction, but I don't think it comes down to Bayesian versus frequentist.
But latent variables is what we Bayesian call the variables that we integrate over. No? So
Bayesian integrate parameters as well, right?
Sure, we integrate all of it. But like basically, there seems to be something magical that you describe to the wording latent variable. How is it different in this case from the variable that, we integrate over it as we do as Bayesians, as opposed to selecting one value. Is there something that goes beyond that you ascribe to the word?
That's right. Yes, our description of the world is that on every trial, something random happens that we don't have access to, right? So the more data that every trial, I'm going to draw that random variable from some distribution, and I'm going to use that hidden latent variable to generate my data. In a Bayesian analysis, I would treat the parameters as latent as things that I would integrate. The parameters as random. I'm not saying that, but here we have a fixed number of parameters, and as I get more and more data, the parameters don't grow with that data set. So what I'm calling latent variables are. I think it's a standard.
Just call it, if you're Bayesian about something, you call it latent variable. If you do a maximum likelihood fit, you call it parameter. No?
Okay, now I want to bring in other parts of the audience here. I think that I'm sure Errol must have some question or comment.
I have to say, I'm hearing both of you talk. It's very interesting. But it makes me like, first, I don't trust anything where the result comes down to an argument about statistical validity. And so I'm at this point, I'm not sure I trust either one of you.
I'm just trying to trust myself.
So Conrad thinks I'll trust him more if he hands me a microphone. So I'm a little bit concerned about that. But I will add that I like Jonathan's point just now. I think when you don't have sufficient data to really cleanly constrain whether we call it a parameter or a latent variable, I don't want to get into that debate. When you don't have enough to really strongly constrain it, then in my experience, it's very easy to get into situations where plugging in a point estimate is going to give you something very biased and will completely screw up the answers that you're getting. And I think that's what went wrong in your initial analysis content.
Right, and I do like the Bayesian cross-validation approach that Jonathan's doing a lot, just to be clear.
Can I ask?
So building in other sources of variability seems critical to me in this problem. One is taking out of the problem the variability that's coming from the stimuli, which I mentioned earlier. That to me seems absolutely critical. That's a really, really strong piece of input, which at the moment is being treated as random, and it needn't be, because you know what it is. The experimenter put the dots on the screen, the dots moved in a particular way, and so building that into the analysis, I think, can go a long way toward resolving some of the issues and cutting out a lot of the noise that's basically making it hard to estimate anything.
But you might need a model of the visual system to be able to model those things out.
No, I don't think so.
Arrow,
I think
do
you
you
can do
think
something very simple.
you think the Fano factor would go down if very significantly if you plugged in the?
No, because that's the other big source of variability is internal state, and I think that you're going to have to live with, and you can start to build more and more sophisticated models that include fluctuations of internal state. But then we're going to get back into a game of worrying about whether we have to integrate over those. Which is, if you keep trying to integrate over more and more of those things, eventually you will get nothing out of the data. So I think it's a path that's dangerous.
It's the opposite of that. If you integrate them out, you won't have a problem. If you try to fit them all, I mean, we're talking about fitting a model with hundreds of parameters versus a model with 10 parameters. So I think it comes down to that. As you get more data, you don't get higher SNR. You're basically adding parameters for every trial, is what I would say is. So if you can integrate
That's why you're saying you need to integrate them.
That's right. That's the only game in town.
If it's possible.
Yes.
Okay.
I'm wondering if either of you is considered a hybrid model. So you can think of the step model and the drift diffusion as being sort of opposite ends of the spectrum. And there's something in between. So I know, for instance, Paul Mary's looked at this with Jeff Schall's data in terms of, and he found that the leaky competitor accumulator model provided a better account. And that will capture more of a step-like dynamic without going to the full extent of a discrete step. And so if the ground truth is somewhere in between, you might end up favoring one of these models for kind of arbitrary reasons.
Yeah, Nathaniel Dahl made a similar comment on Twitter to say that, yeah, we can imagine a nested model where, let's say, there's a slope of the ramp, and it starts at a random time. So now you could basically extend from a ramping model where it starts at the beginning of each trial and it has a shallow slope versus one where the time is variable but the slope is very steep. The problem is that the reason that won't work, at least for the model that I described, our stepping model for 0% coherence can step up or down. Right, so you need an additional probability so the slope would have to be stochastic on each trial. It couldn't be a fixed slope. So anyway, but I think it's a great point. Is if we could move it into a larger family of models where we could, we would be on some continuum between pure ramping and pure stepping. That might be I don't know the model you described, but I think I'm all for that.
And at some level, you could set it up as a generic machine learning problem where you say, I want to solve that estimation problem, and I can basically allow arbitrary functions. If you regularize heavily, that will also work.
Yes.
I might be too quiet without a microphone. So I implemented your model, and one of the things that I found, no, not yours, yours was complicated. So when I simulated your model, I found that it was very difficult for me to retrieve the step times that I myself input into the model, and I don't know if that would be different for the more complex stepping model. So I was wondering what the reason is to not take into account more factors that would constrain the analysis. Say correct responses, I believe, and usually those experiments are not done in a reaction time environment. So there are all of these other potential behavioral correlates that, if we believe at all that LIP relates to this behavior, they should be reflected in some point. And I know that the usual argument is that step times occur random within the population, but still there should be some connection to the behavior, and yet if the population represents the ramps that we're measuring over different trials. So I was wondering what your opinion on that was.
Okay. Now there's two great points you made there. One, so I will make a plug for Bayesian methods now, which is that, so an advantage of considering the full posterior distribution is that we're not trying to identify what was the step time on that trial. We get back the full distribution over when the step times would occur. So we might find that for some trials, we have massive uncertainty. It could have been early or it could have been late. So here's some inferred latent trajectories under the stepping model from real data, right? So from this trial here, you can see that there's this amount of uncertainty about when the step time occurred. That's given those spikes. Here's one where it could have been an early upstep or a late downstep, right? So the nice thing about this is it gives access to that distribution. You're not left with just saying, the time that I think the step occurred. You're throwing away a lot of information if you're trying to think. So I guess if we look at our method, you should be able to not recover the exact step time, but you should be able to recover a distribution which includes the true step time among it. And then we would see that as you increase SNR, let's say if the height of the step gets higher, your certainty. Now here's one where there's relatively high certainty about when the step occurred. And we can do the same thing for the DDM, right? So these are samples from the posterior over the latent variable given the spikes. So the spread of these is kind of giving us some sense of how confident we are, right? We don't know from this, this spike rate to this spike rate on that single trial, but it's better than maybe asking for the single most likely trajectory, which is that black one. The other point that you made, I think, is a great one, that nothing I did had any link to behavior. So we treated these as spikes that we put into our statistical machinery and outpopped, an assignment of one model better than the other. So Conrad was looking at correct trials only. We were looking at all trials, so we actually had the case that the animal might have gone to the preferred side, but we inferred step time went to the left. I think a more interesting way is to take the behavior and the neural data and build one model that would combine the two.
So but the question is always then, yes, you can't figure out what the switch time is. And at some level, it's nice to have that posterior. The problem is that it's unclear how we should think about the posterior. For example, if it goes the way that it jumped down, it could just have been that there's something outside of what my model meaningfully described.
Absolutely.
Which is
model mismatch
early on that we didn't have later on. So
we agree.
So I don't disagree about it a lot. I mean, look, this idea of integrating out the models that makes your fits more robust to it. At some level, it's a way of dealing with that sparsity of data. But I agree with Arrow that at some level, I'm not willing to bet on any of these things mechanistically because it's just too hard to provide any certainty about it because we have model mismatch, and on top of it, we can't say things cleanly on individual charts.
So one last question, we'll go in for coffee.
Okay. So Conrad made an interesting statement about neuroscience is not looking at the residuals of their models often enough. And I think it's a really good suggestion, but very often, I think there's a good reason why they don't look at the residuals very often. And precisely the reason you pointed out in one of your slides is that you eyeball the rasters for a lot of these data that are low spike rate, low SNR. It's very difficult to tell what's going on, and very often if you're looking at residuals, these are continuous rate models, and the spikes, there's 4 or 5 spikes, so the residuals are kind of like garbage. And so, and also for models like Jonathan's, it's very difficult to know what the residual counts as. So I'm wondering if you thought a bit about what do residuals in these kinds of models mean and how do you interpret them?
So at some level...
Did you define residual, maybe?
Yeah, so the residual is just for people who haven't used that term before. So you take your data, you fit a model to it. Your model won't be perfect, ever. And you can then look at the differences, like how do the two of them differ, and see if there's structure. So if your model is correct, then there might be noise in the residual, but there shouldn't be any structure. So if you look at the structure that's there, at some level, it's a modeling approach. So how do I believe models are wrong? For example, if we have a model that doesn't have spike history, I might expect, well, if my model was correct, then there should be nothing, the remaining autocorrelation function should be flat. If I believe that maybe behavior doesn't matter, then the correlations with behavior should be flat. If I believe it's linear, but I have doubts about it, I might ask, well, is there a correlation between the square of that signal and the residual? There are all those things. At some level, when we look for residuals, we look for like hunches that we have, how the biology as we understand it may deviate from the models as we're building it.
Yeah, I mean, I would just say, to add to that, single trial residuals would probably be meaningless, but I think Conrad's point, autocorrelation. So looking at averages of residuals or moments of residuals, and I think that's another point we agree on, is that exploratory data analysis, I meant to say I didn't disagree with everything in your talk, just most, but yeah, exploratory data analysis of finding interesting ways to plot your data, hold it up this way and that way, project it on different dimensions. We don't yet know what's going on in these data. That's often the important step to discovering new things that we didn't know were there. So actually also building tools for exploratory data analysis is something that both Conrad and I have worked on a lot as well.
Yes. 10 minutes, newly caffeinated, we'll return to hear the final word from Mike.